Okay, hello again, everyone. I hope you can hear me well. And now I'm going to introduce this work together with Sylvan about evaluating machine learning workloads on a memory-centric computing system, which is the UPMEM-based PIM system. So you see it has been a collaboration between ETH Zurich, the Safari Research Group, and ABUMPIMP. So we're going to start with an executive summary. First of all, training machine learning algorithms is computationally expensive and frequently memory bound because it needs to access large amounts of training data and needs to access them repeatedly. So processing in memory can alleviate this data movement bottleneck. And we already know that the ABUMPIMP architecture is the first one to be publicly available and commercialized. So our goal is to understand the potential of this PIM system for to accelerate machine learning training. Main contributions of this work are the PIM implementation of several classic machine learning algorithms, linear regression, logistic regression, decision tree, and k-means, the workload characterization in terms of quality, performance, and scaling, and the comparison to their CPU and GPU counterparts. Here you can see some promising results. I think that Sylvan will later elaborate on them. And the source code is publicly available. In our experimental evaluation, we use the ABUMPIMP PIM system with 2,524 PIM cores, and there are some key observations, takeaways, and recommendations that are outcomes of our work. Okay, so this is the outline, and we'll start with briefly describing the machine learning workloads that we are targeting. I will probably definitely skip this part about introducing processing in memory. Then we can talk about the implementation of machine learning workloads, and finally the evaluation in terms of quality metrics, analysis of PIM kernels, performance scaling, and comparison to CPU and GPU. Given that Sylvan is going to present the decision tree and k-means, I'm going to skip the PIM implementation of those workloads as well as the evaluation, and I will hand over to him. Okay, so let's start from the beginning. These are the, as I mentioned earlier, machine learning training is computationally expensive, it requires many iterations, and due to that, suffers from data movement between memory and processing elements. And that's especially bad when we have low arithmetic intensity, low temporal locality, or irregular memory accesses, so that we cannot amortize the cost of bringing the data to the processing elements. So our goal in this study is to analyze and evaluate how promising processing in memory systems can be to accelerate machine learning training. And we target these machine learning algorithms: linear regression, logistic regression, decision tree, and k-means. They all are memory bound according to the roofline model. So here, I think we don't have anything to say anymore. We have talked a lot about, or we are talking a lot about the ABUMPIMP PIM system. This is the one that we have used in this work. So let's talk about the PIM implementation of linear regression and logistic regression. Well, first of all, PIM implementation of machine learning workloads, and let me remind you that these four are, and they have some diversity in terms of memory access patterns, operations on data types, and communication and synchronization. So for linear regression, which is a supervised learning algorithm, here we use gradient descent as the optimization function, and what we do is partitioning the training data set equally in equally sized chunks that we assign to different PIM cores, and inside each of them we compute dot product between the raw vectors and the weights. Then we compare each dot product result to the observed value to compute a partial gradient value, and these are later reduced in the host processor. We created 4 versions of the linear regression. The first one uses real values, so we are using 32-bit floating point numbers. Second one uses fixed point representation. Third one is a hybrid precision version. It starts with 8-bit and then moves to 16 and 32 bits. And finally, a custom multiplication that is based on the 8-bit built-in multiplication that the pipeline has, that the ALUs have. For logistic regression, we use a very similar approach. In this case, we use sigmoid, but the partitioning approach is very similar. In the end, We are again doing a dot product computation, and after doing the sigmoid on the CPU, on the PIM cores, then we return the control to the CPU for the next iteration. Here in this case, we created 6 versions. The first one uses 32-bit real values, and in this case, sigmoid is approximated with Taylor series. The second one is a fixed point representation, also using Taylor series. Third one replaces the sigmoid calculation with a lookup table, and this lookup table might be in MRAM or in WRAM. And then we have the hybrid precision version, same as in linear regression, and the version that uses custom multiplication. So 6 versions in total. For decision tree and k-means, I will let Sylvan to introduce them. And now let me go quickly over the performance results for linear regression and logistic regression. So first of all, evaluation methodology, we have used synthetic data sets and real data sets. Depending on the experiments, for scaling experiments, we use synthetic data sets. And then for comparison to CPU and GPU, we use real data sets. The evaluated systems are the UPMEM PIM system with more than 2,500 cores, and then compared to an Intel Xeon CPU and an NVIDIA 100 GPU. We evaluate quality metrics, performance of PIM kernels, performance scaling, and comparison to CPU and GPU. Okay, so with respect to the quality metrics, and for linear regression, the version that uses real values has the same training error rate than the CPU version, and for the integer versions, we see that the error rate increases as we could expect, but it still remains low and close to the version that uses real numbers. For logistic regression, it's kind of similar. It's something interesting that we observe is that the versions that use lookup table queries are more, have, let's say, more accurate and less training error rate than the versions that use the approximations. That for exactly that reason, that Taylor series is an approximation. And for decision tree and k-means, Sylvan will talk about the quality metrics. With respect to the PIM kernels, what we first did was analyzing the performance of the individual kernels, changing the number of PIM threads, as you can see, from 1 to 24 for all the different versions. Here at the top we have the floating point version, and here we have the integer versions. The interesting thing in this slide is to see how the performance improves for the different versions that we created. As you can already see, the first of the integer versions, this INT32, already saves, like, let's say, 1 order of magnitude in the PIM kernel time. That's because there is a large difference in the execution time of floating point numbers or integers. So the first key takeaway of our work is that workloads with arithmetic operations or data types that are not natively supported by the PIM cores run at low performance due to the instruction emulation. So wherever it is possible, it's recommendable to use fixed point representation. And in this case, that was without much accuracy loss. We also see how the other 2 versions further improve the performance. For example, as you can see here in this little window, 41% improvement from the INT32 version to the hybrid version. So quantization and hybrid support are recommended and definitely can improve performance. And then for the version that uses the custom multiplication, we obtain like 25% additional speed up. So whenever it is possible, it also makes sense to use the custom operations either by the programmers or compilers to optimize it. For logistic regression, the first, say, impactful performance improvement that we see is when we move to using lookup tables. It's like 53 times faster than the version that uses approximation. The recommendation is to use pre-calculated results in lookup tables to accelerate performance. This is something that makes a lot of sense in processing in memory because we have a system that is rich in memory accessing this memory is at low latency and high bandwidth. So what this thing that we are doing here is being explored in many other types of processing memory as well. And then we see the additional 28% improvement from the hybrid version and 43 more for the version that uses the built-in multiplication. And this is just to highlight how the scaling inside a single DPU, as we already know, performance usually saturates at 11 tasklets. That's the case in all 4 workloads. So the recommendation is to keep the pipeline fully busy wherever is possible. These workloads become all compute bound, even though they are memory bound in the CPU. Okay, I also have this slide about performance scaling. In the paper, you can see the strong scaling and weak scaling analysis. Here in these slides is only strong scaling. This is for all the different versions that we generated, the 4 versions of linear regression here, logistic regression here, and here we have decision tree and k-means. As you see, scaling is pretty good in all cases. The kernel time scales linearly. Another good thing and good observation is that there is very little overhead from either PIM core communication or the data movement between the host and the PIM cores. As you see, data transfers are basically negligible. Only you can maybe notice them there in their PIM communication, but still the maximum number of PIM cores produces the same result. And I think that this is a good observation because we are very concerned about the data movement to the PIM cores and also the communication between the PIM cores that can really be really bad for some workloads, but these are important, interesting workloads, and as we see, they can perfectly tolerate these data movement. Okay, so yeah, that's my key takeaway. And then finally, for the comparison to CPU and GPU, here I have comparison results for linear regression and logistic regression. In both cases, the GPU is faster. The A100 GPU is faster because GPUs have been optimized for computation, or their hardware has been optimized for decades. But still, let's say the positive outcome or the positive observation is in this slide is that the optimizations that we applied really made a difference, as you can see, and they are faster than the linear regression or the logistic regression, are faster than the CPU, and we also managed to close the gap with the GPU implementation. So that's all from me.
Right, so as noted, roughly speaking, there are 2 categories of machine learning algorithms: supervised learning, where the that you train an approach, and unsupervised learning, where you don't have an output, you just train to extract some sort of structure from the data. So the idea being, let's look at one approach. For unstructured, unsupervised learning, so we've got there is pretty simple algorithm. You put a bunch of points, you pick a number of random centroids to start with, and then you assign each point to its closest centroid, and you've got clusters. Then you move each centroid to the middle of this cluster, and then repeat the operation, and eventually you're going to converge for distinct clusters that belong together in some sense. Right, so that's what I just described. That's what you're doing on the CPU. So you find the centroid for each point, then you sum the coordinates of the data in each cluster, then you get an average, and then you look back until the conversion. On DPU, you're doing really the same algorithm. It's a part of it is going to be parallelized. So you've got your CPU acting as a coordinator, is going to tell all the DPUs, hey, here are the current centroids. Then each GPU has a slice of the total data. It's going to find for each point which is the closest centroid. So that's the most computing part. then it's going to do a partial average, and then the host is going to take those partial averages and finish the reduction, get the new centroids, and reload. So obviously, this part, finding the nearest centroid implies computing a bunch of Euclidean distances. That's not really something we want to do in floating point on a GPU. So we, before starting the whole thing, we quantize all the data as 16-bit integers. So the question is, okay, but is it valid? Does it degrade the results? I remove that. So unfortunately, it does not degrade the results. So to compare the results on the regular algorithm and GPUs, we do two things. One of them is to compute the score, which is Kelvin score, the measure of the quality of the clustering. And we can also measure the similarity of the clustering performed by the classical algorithm and by the PIM algorithm. It's, as you can see, we got on a bunch of random data, and it's always similar, not exactly the same. There are some differences, which is very reassuring because it shows I did not just copy and paste the result into columns. And so, yeah, those differences of just rounding differences, fortunately, we never really get into different local minima between versions. So, let's get some benchmarks, right? So, the real data set with its boson data set, it's popular for that kind of benchmark. It's not a huge data set, it's about 1 gigabyte. So yeah, look at that, it's beautiful, right? But perfect scaling, the more GPUs you use, the less data, the less time it takes to compute, and it's completely linear. And you compare that to the CPU in orange and the GPU in gray. And you end up with a different acceleration. But okay, we did that at the time because that's obvious as a data set, and then the people at PTO finally realized that their data set was not working, so they fixed it. And so we could test that on a bit of a bigger data set. This time, we're taking the critical terabyte data set, it's 30 days, we just take 1/4 of a day, because that's all that's going to fit on a GPU. And also, because this time we have a beefier data set, we also take a beefier library for comparison, because before that we were comparing scikit-learn, but scikit-learn is not a performance library, fortunately. Intel has done an extension for it that's more performance. And that's the real thing. And now you can see, okay, we still get a bit of an increase, but we have to use an entire server for that. Against something that the CPU can do. Is it worth it? Maybe if you look at the energy, it's for you to decide. But okay, it's a bit surprising when you see that. When is the CPU so good even compared to a GPU? I mean, we can do an experiment with dimensionality, right? We generate several synthetic data sets. And the idea is we keep the same total volume of data, we just change the dimension and see what happens. And we see that, generally speaking, the higher the dimension, the better the CPU performs compared to us. And I mean, the reason for that is really simple. When you're benchmarking games on CPU, you're benchmarking another thing. So this is just AVX doing this thing, right? Yeah, it's not surprising when you're multiplying fig matrices on CPU, you're getting pretty good performance, even better than GPU sometimes. So let's try the other one, right? Decision trees. I mean, everybody understands decision trees. You start with several points, and then you try to split them according to some criteria. And now you've got a new leaf, and then you repeat the process until you build the tree and you can't split the leaves anymore. And you evaluate several criteria at each step. You pick the best criteria. So that's the thing. You look at the leaf, you evaluate all the splits you can do on that leaf, you commit the best splits, you cut your leaf, and you repeat, and you do that on the CPU traditionally in a depth-first fashion, mostly because it's more caching. So on DPU, you do the same thing, but instead this time, because we want to parallelize as much as possible, we do that in a breadth-first fashion. So instead of doing the leaves one by one, we work on all the active leaves all together. So this is the CPU. It's looking at all the leaves. Say, hey, have we evaluated the split yet? If not, we need to evaluate that. If yes, please commit that. When you prepare the list of instructions to send to all DPUs, the DPU does the work on all the leaves, and then results are aggregated, and then you repeat until you split the whole tree. In that case, the host doesn't see the data at all, but is the only one seeing the tree that you're building. So in that case, we can also look at the accuracy, so what we did. It's not really necessary in that case because for decision trees, we don't need to do any sort of quantization. With floating points, you can do comparison of floating points in just 1 cycle, 2 cycles. So let's look at the results this time for the same dataset, the X dataset. It's a bit disappointing, right? Not my product for. We're completely saturated. We even have a bit of negative effects by having too many DPUs on your cylinder. It means, we're getting completely eaten alive by synchronization costs and static costs. So if it's not very clear, it's a gray line if you repeat the GPU. So, yeah, we're not in the right way. We could try to fix that, or just look at the figure. So, same thing as earlier, one more for the video, and this time that's a bit better. We're getting still not linear, but pretty good scaling, and now we are using the green GPU line. This time I thought we compare to detail. So yeah, we are on par with the GPU now. But as we see, we're still not in the ideal regime, we're still in saturation. So we can go a bit further away. We can go to the data domain where the GPU cannot operate. This time we take 2 days of video data. So that's a 64 gigabyte data set. We can't compare to the GPU anymore because it doesn't work in that range. And this time, yeah, we've got some really good increase compared to even the optimized CPU implementation. So what are the lessons from that? Well, first off, yeah, it's about arithmetic intensity. If you're going to develop a GPU application, you have to ask yourself, does it look like a matrix multiplication? And if so, it will be not a good candidate. The second one is really, generally speaking, you want that performance, you want to fill all the CPU with data. So maybe you have a big data set, that's the simplest case. If you don't, there are other ways to do it. You can either run different processes in parallel on a subset of GPUs, or you can even do some, if you have one job to do, you can do some data application, which is something done with the ARM, so that each GPU has more work. And that's the thing.